Hi, it's Roy again. We're starting a build with a TJ07, and this is a custom build. We're running an i9 7940, 14-core processor in this. I'm going to use a 480mm radiator to cool that CPU because I intend to overclock it pretty hard. This radiator is made by Hardware Labs. It's the top end radiator that I can purchase. It's 480mm. It's got a very low fin density. It's 9 fins per inch, and this allows me to use some very low RPM fans to obtain the type of cooling we need. Before we can get started by fitting the radiator and putting it in, we have to flush it out. Even though it's a brand new radiator, all radiators have some kind of debris in them, and I've seen some that were absolutely filthy. I've seen others that are pretty clean, but they've always got something in there. It's a remnant of the manufacturing process, little bits of flux and sometimes solder, little bits of debris. We intend to put an inline filter in this system. This is a very high-end system. It's going to have all the protections available. However, prior to doing that, we want to make sure this is clean. Now, the typical way that radiators are flushed is that you fill them with distilled water, you shake them up and down to loosen any debris, and you drain them out. Well, we've done that a couple of times with this, but it's been my experience that that's usually not enough to really completely flush a radiator. So what I do is I've got a 10 gallon per minute pump. I've got a gallon of distilled water. I put in an antibacterial a biocide called dead water in there because I don't want to let anything grow in this radiator over the next few days while it's sitting around with moisture in it. I've got a filter here that cuts down to 5 microns. So the object here is to pull water, clean water from this reservoir, go into the radiator, blast it through the radiator, come out, catch any particulate matter in this filter that is just being discharged from the radiator, and then blows the clean water back into the reservoir. This is going to cycle through, and I'm going to let this run for about 15 minutes. Now, 10 gallons per minute is about 5 times faster than the fastest PC circuit, water cooling circuit there is, at 2 gallons a minute. This will just expedite the whole cleaning process. So I'm going to get started with this, and then come back in about 15 minutes, and we'll see what we have. Also, I've got this hose, the exhaust hose set up so that it's splashing in this bucket, which creates cavitation. I want to pick up some of these air bubbles because they act like little ball bearings flying through this radiator, and they help loosen things up as opposed to just a smooth stream of water, which I could get by redirecting my hose to a different position. You see how that's smoothing out? But I like the cavitation, so we'll let that run for a bit and see what we get. Okay, this has now been running for about 25 minutes. I'm going to shut it off, and I'm going to check out my filter and see what I have in there. Purge my filter. Oh, this thing's really tight. Okay. We'll probably get a little bit of water on the floor. That's okay. There we go. Yeah. All right. I'm going to take out the actual filter element. I'm going to put it in a pan over there on the side. I'm going to pour out the bulk of the water on top. Yeah, I've got a little bit of debris in here. All right. I'm going to pour it through a filter paper so we can I want to get this stuff right down on the very bottom of this filter. There we go. All right. Oh yeah. So now I'm gonna bring the camera over so we can, or actually I'll bring this to the camera so we can actually see what's in here. There, you can see the debris in the bottom of the filter there. Little bits, little tiny bits. Well, we're gonna run this thing through again. And we're going to take it, try it, and see if we can't get a clean pass on this filter. So I'm going to stop the video now and run it through with clean water, and we'll see what we get. Okay, this is the second pass on this radiator. It has been running now for about another 20 minutes. We're going to open it up and we're going to get an idea of what's inside. Now we've got I put in, topped off my water. I cleaned and rinsed the filter compartment out and the filter. So basically it was starting from scratch. So now my filter is clean and dry, and now I'm going to put in the second load and see what it looks like. It should be pretty clean. And we're putting through it 10 gallons a minute at 20 minutes. That's 200 gallons. We've done this twice, so we've run over 400 gallons through this radiator already. Yeah, it's absolutely pure. Yeah, this is really clean. One of the reasons we absolutely must do this is because the particulate matter that comes out of this could clog up some of the tiny lines inside the CPU block. And on this particular machine, we're using a mono block, which will cool off the VRM and the CPU. This is made by EK Water Blocks, and we don't want to risk plugging that thing up. There is not one tiny fleck of anything in this filter. It is absolutely pure. The bottom of this is totally clean. We've succeeded in flushing out this radiator. This is a bit extreme, but if we have the opportunity to do it, it's better to do it now than to put it in the system and hope and pray that we don't have contaminants floating into our loop somewhere. As I mentioned before, there is a really nice removable screen filter from Aqua Computer that's going in this system, so that if there are contaminants introduced into the system, then it will catch them and they can be easily taken out without having to drain the loop. And, I'm here to talk to you a little bit about this case we're going to use for this build. This build is going to have, and I'll go over all the details of the parts later, but just in an overview, it's a 7940X, and we're going to overclock this thing pretty hard. We're running twin 1080 Ti's in an SLI configuration, a 480 millimeter Hardware Labs 60 millimeter thick radiator in the bottom of this thing, dual EK D5 pumps, PWM pumps in series. So this thing is going to be packed, along with a reservoir and a few different bay devices. Now, we chose the TJ07 because it kicks ass. It's just a beautiful case, all in all. It's made out of one single piece of aluminum. It's punched out of a unibody press. It's as thick as 8 millimeters. It's built, it's overbuilt. It's put together with machine screws and not rivets, so that it's designed to be modified really easily. It separates the power and the radiator from the rest of the computer, so it's just perfect for water cooling. It is absolutely top quality. Now, it's also very expensive, but it also, to bring it to modern standards, we have to do a fair amount of machining and work to this thing, because this thing won the Maximum PC Dream Machine Award for the year in 2005. So that was 13 years ago. So there are a few things we need to do to bring it up to speed. Let me go over that. I'm going to pop the covers off so we can get an idea of what's inside here. These covers are steel with aluminum vents on the bottom for the water cooling to go. This is the back of the motherboard. Hey, there's a box of hardware. Toss that over there. This is the windowed case, the windowed panel. Again, it has the vents on the bottom for the fan. Now, this has a removable motherboard tray. The whole back and the tray come out. And I'll take this out for just a minute. One of the things I really love about this box is that it's designed to be worked on. There's not a lot of room for wire management behind the motherboard tray, which makes my job of a clean build that much more difficult. And I'm going to show you how we're going to get around that in just a second. So this entire motherboard tray slides in and out with the back of the PC. Okay, so I'm going to pull this out. Now, this motherboard tray, steel tray, it's got lots of holes in it for different kinds of motherboards. What we're going to be using, Asus's top of the line ROG motherboard. It's an EATX motherboard, so it's not going to fit perfectly on this motherboard tray, and I don't like these extra holes. So we're going to make an entirely new motherboard tray, and we're going to make it out of 1/4 inch thick aluminum. I'm going to powder coat everything inside, sort of a matte texture black, and I will also powder coat all this in the back. I'm not going to do anything to change the fan orientation, but I am going to clean everything up and paint it. That being said, these fans down below with these are hard drive cages that come with it. These are to house your old platter hard drives. On our new motherboard, we're having M.2 hard drives. We'll have a few SSDs up in here, so we won't need these, but we do need the space for our big radiator and our water pump down below. So these are going to disappear. The inside of the case is going to be covered with an acoustic material so that no noise will transmit out. And this will be our radiator and our pump and our power, big 1300 watt power supply. And what I love about it is it's got this panel in the middle which separates the motherboard with the graphics cards and the VRM from the heat from the radiator. So we've got two separate compartments here. I'm going to take this divider in the middle and completely cut it out. It's got two issues with it. One, we don't need all these little openings in here. We're going to completely close this off. There needs to be some access for wires to come through behind the motherboard, which is going to be in this channel here. So all this will have to be cut out. Basically, we're making a new piece for this. The front panel was designed for USB 2 and FireWire, which nobody uses anymore. So this is coming out. All these are going away, and we're going to replace it with a USB 3 and add the USB 3 Type A and add the USB 3 Type C as well. Sort of modernize this a little bit. The fans that come in this box, gone. We're replacing them with Noctua fans, the best you can get. I'm going to build an aluminum panel that goes here to hold a 140 millimeter fan. We're only going to use 4 of these 7 ports for bay devices. These 3 will be replaced with a grill that will allow for air intake for a 140 millimeter fan. I want some more air intake. There are 2 120s up here on top, 2 92s for exhaust, but I want that 140 to bring air in through the front. So we're sort of redesigning the airflow on this. It's also going to be a mix of color. This is a beautiful, it's a bead blasted aluminum that's been clear anodized. It is absolutely gorgeous. Our bay devices are going to end up being, for the most part, black. We're going to have a slot load DVD Blu-ray. We've got a card reader. We've got an electronic display that will give us our water pressure and water flow. So those are going to be black. Our vents will be black. So it's basically going to have a black stripe down the front. On the top of this, let me tilt the box for you. The top of this has a beautiful inset aluminum grill that covers the fans. I'm going to powder coat that black as well. All these panels inside are going to be powder coated. And I will also make a cover for this so that I can put in my clone drive switch and a few other things. And you're not going to see the standard cutouts for all the holes, especially the fact that we're not using them. Let's see, the motherboard side is essentially going to remain the same. This is going to be hidden. Again, we'll add our acoustic material, our pump. This will be where the exhaust is coming out from the radiator. That's about it. So the next time, oh, and then also too, on these panels, I'm going to powder coat these black as well. So it'll have that sort of a two-tone black and silver look to it, just to give it a little bit of something. And once those panels are produced and powder coated, we'll go ahead and put them into this case, and you can compare the differences. The next video I'll lay the panels out after I have them, and you can see the difference. Okay, Jason, this is for you. This is your computer build. This is a one-off. I'm not doing this again. It's specific to your unit. This is the TJ07. In fact, this is going to be so cool. This is like totally nerd porn. Okay, I'm putting on my nerd porn hat. Now, this thing here, the original motherboard tray, as we talked about, it's steel, it's a hollow back, it's got lots of holes in it. For a standard size motherboard, these are your Silverstone fans. Other than that, it's pretty generic. So what we did, we changed things out a little bit. This motherboard tray is about 1.5 inches longer because there's this stupid little space in the case where there was no motherboard tray and the motherboard stops about here, and I just wanted to extend it to make the case look cleaner. I've also done things like I put in slots in this motherboard tray so that my SATA cables can come through and my big 32-pin power cable can come into the motherboard here. There's also a cutout back here for behind the CPU that wasn't on the original motherboard. These are a few things that we're bringing it up to standards. This was designed in 2005 and now it's 2018, so things have changed a little bit. Also the fans. We've upgraded these to these Noctua fans. These things really throw out a lot of air. They're also guaranteed for 6 years for constant duty use. They're extreme duty cycles, whereas these are standard fans. So that's about it for the motherboard as far as I can. It's 1/4 inch thick, I told you. That's about it. It's all powder coated black texture, whereas this was the original aluminum finish. I did this just because it looks cleaner on your case, and we'll get to more of that in a little bit. Okay, that's it for the motherboard tray. I'm going to go off and start bringing in your other stuff, which will be the plates for the inside of the PC. I'm going to show you some of the differences there, as well as the USB connection. Okay, I'll be right back. Okay, we're back again, Jason. On the TJ07 build, here's where we are now. We've gone ahead and we've got all of the plates powder coated and cut. I want to show you some of the differences we did. This is the factory divider plate that separates the bottom of your case to the top. So your power supply, your pump, your radiators, all the big heat generating stuff sits in the bottom of the case. And this is to separate it from the top, which has a different airflow system, and it has your graphics cards as well as your CPU. So here's what we had to do. We cut out the bulk of this to fit a light, which I'll show you in a minute. We also opened up this whole strip behind the motherboard so that I can run cables and wires to the power outlets and everything on the motherboard without having to dangle wires over it. I don't like the idea of having wires up in front of your motherboard straddling everything like a Dell or something. You know, this is a really clean design. So wire management is critical. Other than that, it's powder coated, solid, one end to the other. The other difference I made on this, and which is really cool, the USB that you had in there this is the original one from 2005. It's USB 2 and FireWire. FireWire is not used anymore. Nobody cares, right? USB 2, it was state of the art when it came out, but look at this mess. This is how you connect to the motherboard. Okay. Your latest motherboard, which is the state-of-the-art world's best motherboard, doesn't even have accommodations for this stuff anymore. Okay, so 12 years later, this is USB 3 with a USB 3C and A ports. Microphone, headphones, real simple. Much easier. One connector for all your USB. Real easy. It's just going to snap into here. Instead of having this snap into here and having to manage this mess, we've got something really clean. Okay, so that's it for the plate that sets the two apart. Now I want to briefly go into the lighting end. Let me pull this away. So what we've got here see if I can orient this correctly. This is the divider plate. This is where your motherboard will ride. This will be the front of the computer. I built a light box for you. There are a bunch of LEDs. Let me count them. 278. Okay. They're sitting underneath white lighting plexi. I built a black surround for it. So the way this works is this actually gets machine screwed onto, let me turn this around in the orientation it's supposed to be. This gets machine screwed to the bottom of this divider plate. And then the light cap gets put on here so that when we turn this on, we now have a really beautiful diffused lighting that comes up through the case. You can turn it way down or you can crank it way up. This shows off the workmanship and the quality of the material they have inside without all the LED bling bling stuff. That's not my thing. But I just thought you'd like that. So we're going to go on to the case and the internal plates next. Okay. Okay, Jason, we're back again. Back on the TJ07 build. More nerd porn. This is the plates that are going to go together on the inside of the computer. The original plates that came with your TJ07 are beautiful. The aluminum, but they're raw material. They don't take paint very well. It doesn't stick to aluminum, so these things had to be powder coated. So here you go, Black Tex powder coating. These are the upright plates that hold your 5 1/4 inch drive bays. So when you put these together to hold the drive bays, one of these is visible, the one on the windowed side. And what I didn't love about it is that you can see all these holes for the drive bay covers that you may or may not be using. And even if you are using them, I don't want to see a selection of hardware sticking out. There's no reason for that. So what I did was I cut a piece of 1 millimeter thick aluminum plate, powder coated that, and then shaped it to fit the contour of the TJ07. So when it goes in, you've got a nice clean cover that conceals all those little bolts, so you're not looking at that hardware unnecessarily. It's just a little touch to make it pretty. Now, when these go in like this, and we want to bring a fan into this to bring some air intake. So what I did was I cut a piece of 1 millimeter thick aluminum again, and I put a Noctua 140 millimeter industrial 2000 RPM fan on this thing. This will draw lots and lots of air in. It will be controlled by your motherboard so that you can set the fan curve based on the case temperature. It's gorgeous. When your case is cool, the fan doesn't run. It's really quiet. When the case gets hot, fan kicks in. It cools the case. Now, that will sit between these two plates. Inside your case, it's going to, again, be very clean. This is going to give me some places up here to put like your clone drive switch and maybe a temperature gauge setup. We're going to really deck this thing out. So then, bringing air into the case, got to be filtered. This is the original cover plate that went on your TJ07. There's like 7 of these things. We're going to take 3 of them and we're going to replace them with these aluminum cover plates. Black anodized aluminum, they're drilled, and they have filter mesh behind them. So that the air coming into this case is going to be clean and filtered. We don't want to be bringing garbage into the case. Dust bunnies aren't good. So that will help that out. We'll go over that more once we get the case assembled. You'll be able to wrap your head around exactly how that works. The rest of the stuff is pretty basic. The uprights and struts that are the structural bone in the back of this case. So this is the prior to being powder coated, and this is being powder coated. So they're powder coated, and then all the holes that had threads in them had to be retapped so that the powder coat doesn't foul the threads. Fair amount of work in this. Now, power supply cover, right? It's in 2 pieces. You got chrome and aluminum. Kind of funny that it's kind of 2 pieces. So we took them apart and we powder coated both of them, so now they're more homogeneous, a little bit cleaner. That's that. Your top fan housing, okay, it's the screen configuration. We powder coated it black as well. But you've got these old Silverstone fans. Now, back in the day, they used Molex connectors, which suck. Nobody uses Molex anymore. And they've got these little tiny wires to give you to tell you what the RPMs are on the fans. Now, I'm going to replace these with Noctua 2000 RPM industrials. That the motherboard now, the motherboard you're using has all the capability in the world to set fan curves for these fans independently. So we're not using all this junk anymore. We're using a single PWM wire coming off the fan. So that's going to be powder coated black, and the fans are going to be changed. These are simply for the bottoms of your doors, and we're doing these black as well. That's about it. We're going to get into putting everything together in the case. In the next video, I'm going to show you the case assembled with the lighting and with the black plates and everything. This is going to be nice. Okay, back again with the TJ07 build. As I had said last time, we were going to put the plates in the actual box to get fitting. So I've gone ahead and I put in the uprights on this. I put one panel on so you could see what that looks like with the blacked out vents. Blacked out vents on top. These are the front vents that are just laid in place right now. I went ahead and I added a few things. I put the motherboard tray in. I put the standoffs on it for the motherboard. I added a temperature display here so that we've got a temperature display in Celsius for the water temperature and one for the air temperature in the case. This way, just at a glance outside, you can see what your temps are running. Normally, you click on an application when you have Windows open that will give you, it's a hardware monitor application that will tell you everything that's going on with the machine. But I like the idea that I can just look at it and say, get an idea what the temps are running. So here's the aluminum cover plate for your 5 1/4 inch bay devices. That's it. Everything is set up. It's going to be ready to assemble. I'll show you what it looks like with the front cover on, roughly. This is just to give you an idea of the orientation of this cover. So the cover hides the basement and basically just reveals the center part of the computer here with your motherboard, your graphics cards, and your base light. We're ready to start the build. The next video I'm going to cover the components that are going to go into this system, and then I'm going to do a layout of where we're going to put the reservoir, how I'm going to run my cooling, how I'm going to run my wiring. So all this has to be mapped out before we actually start building so that we're not guessing as we go along. That's it. I'll get back to the next video. Build. This time I want to go over basically the components, the basic bones that are going into this system and why. I'm designing this workstation for a few things. One of them, I want extreme reliability. So I'm incorporating the very best parts that money can buy that are known to be extremely reliable. It's important that this thing be a daily driver 24/7 and not have an issue. Along with that, we also want it extremely fast. So in order to do this, we're pulling out the stops with the processor, and we're also overclocking this, and I'll go over the details in a bit, but we want this thing to be ripping fast, and it's based on the type of software that we're using. It's the composite software like Zareen and Helicon. It's also the image processing software like Phase 1 Capture One, which uses a GPU, and this is why we're going GPU heavy on this box. We want to super cool this thing. We also want a redundant backup system in it so that if a system fails, there's an automatic backup that kicks in. So it's not that if something burns out or if it fails, you have to stop and shut the machine down and find a part. You want to be able to kick it in right away and then deal with fixing it. It's a zero downtime that way. We also want this to be very quiet and maintenance free. So a lot went into the design of the cooling system so that it is extremely efficient and extremely quiet, down to the types of fans we're using, and I'll get into that in just a minute. But there are hundreds of hours have gone into figuring out what components work best with each other and why. And so when you're trying to get a specific goal, you pick from a specific list of components that will best achieve that goal for you. And this is what we've done here. Also, we want it to be aesthetically pleasing. It's functional art. There are many, many man-hours that go into building this thing. And we're very proud of what we do. So not only are we using the best materials, but we're trying to showcase this in its best possible light. And that's why we chose the TJ07 solid aluminum case and why we've done the custom mods to it. Because when it's all said and done, we want it to be tasteful and clean and classic and just solid for years to come. So that's it. Let me start with the basics. Where we're going with this is the motherboard. That's going to be the first part of this. And what we've done is we've chosen ASUS's flagship motherboard. It's the Rampage 6 Extreme motherboard. This is arguably the finest motherboard made. This is for the X299 platform. It outperforms virtually everything else that ASUS produces, and ASUS is the world's leader in motherboards. This thing is such a tank. It is so overkill. It even has accommodations for if you wanted to use liquid nitrogen cooling. It has water sensors. It has everything on it. It is also, it costs anywhere between 3 and 4 times the price of a standard motherboard. But there are reasons to have this. It's designed for overclocking. It has features and functions on it that we would have to buy aftermarket hardware to accomplish. It's just gorgeous, absolutely gorgeous. It's my pleasure to be able to work with something like that. So what we're going to do is we're going to plug in. This is the CPU we're using, and this is the Core i9. It is a 7940, 14 core. Now, what we're going to do with this is we're going to do something a little bit unconventional. We're going to delit it and we're going to lap it. And what that means is that we're going to pop the heat spreader off the top of this, and we're going to replace the thermal paste that Intel puts under here. They use a material from Dow Corning that it's okay. It's very reliable, long-term, long-lasting, but it doesn't do a terrific job of transferring the heat from the actual die to the heat spreader. And we need to transfer the heat from the die to the heat spreader and from the heat spreader to the water block to get the heat off of this CPU. The better we can get the heat to pull off of this CPU, the less stress on the cooling system, the cooler we can run it, the better overclock we can get, the longer it will last. There are a lot of reasons that this is a good thing. So what we're going to do is we're going to take the top off of this, and we'll videotape this, where we will remove the paste that Intel has put on this, and we will replace it with material called liquid metal, which has a much better, it conducts heat much better than the thermal paste does. We're going to put this all back together and seal it up. Before we do that, we're going to lap the front of this CPU, so the heat spreader will be bare polished copper and not nickel, and it's going to be absolutely flat. Again, anything we can do to help it pull heat off the CPU is what we want to try and do. So, as far as the memory on this machine, we're going to be running 64 gig of G-Skills top-of-the-line Trident Z memory. This particular memory is on the approved memory list for ASUS for that motherboard. So it has already been approved by ASUS. They know it functions, and it functions correctly. This is 3200 megahertz RAM with a latency of only 14, which is extremely low. This is super fast DDR4 memory. I'm using 16 gig modules so that this motherboard can accommodate 8 modules. If in the future you ever wanted to add more memory to the motherboard, you could add another 64 gig and have it take a full 128. It is absolutely unnecessary in its current configuration, but rather than load the memory slots up with a bunch of 8 gig modules, I went for the 16 gig so that you do have the ability to expand later down the road. This also has an XMP profile built into it, which we'll get into later when we start the overclocking. And it's designed to function again with that motherboard. So this is about as high as you can get right now for this motherboard effectively. For the hard drives, the boot drive is going to be a Samsung 970 Pro M.2 SSD. Very, very fast drive. The clone drive for this system is going to be the Samsung 860 EVO. Again, as a clone drive, it sits in the box with the power off. It's never used until the day that you absolutely need it. And then it's an exact copy of your hard drive with all of your applications and your settings and everything. So you turn it on and you just operate like nothing's happening, and then you can replace this drive later. The primary image drive. This is a 2 terabyte M.2. It's the 970 EVO. And what this is unique in that this motherboard has the ability to take an M.2 SSD, bypass the PCIe lanes, and go directly to the controller on the CPU. And that's exactly what we're going to do. There's zero latency. It's blazing fast. And here's another 500 gig SSD. This is going to be for a removable front drive so that you can shuttle data from one place to the other. The front drive encapsulates this in a container that has a USB 3 port on the back. So when you plug it into the front of the machine, it's running off the SATA connection at 6 gigs per second, so it's really fast. So you can pull large files off. And if you wanted to take it home and plug it into a laptop or another computer, it's got a USB 3 connection on the back. You plug it in and you can offload your data like a shuttle drive. So that's it for those. And then when it comes to storage on the machine, you've got a 2 terabyte for your primary image drive, which is where you're going to put all your images as you're working on it. But for storage and for backup, I'm including a 10 terabyte Western Digital Gold. This is a enterprise class server drive. This is designed for full-on 24/7 use. And it's 10 terabytes, so that'll hold you for a little while until you decide you need more. And then there's room for another 6 hard drives on this machine if you care to use them. Okay, let me get into some of the basics of the power supply. This thing draws a lot of current. It's going to have a couple of, before I do that, we'll get into the graphics cards. We're using 2 of these. These are EVGA 1080 Ti's, as you can read on the box. This is FTW3 cards. These are, they call For the Win. These are high-performance pre-overclocked cards. We can still overclock them. There's still some headroom on them, although we won't need to. They are incredible for what they do. So we are going to stick 2 of these things together in an SLI configuration, and this thing is whipping fast. Now, they are fan cooled, so we need to have some airflow in that case, and this is why we're addressing this with Noctua hydrodynamic fans that are designed to last for 50,000 hours, and they're silent. This is why we love it. So this is about, that's the fastest card on the market, period. We've also got some connections here for the EVGA cards. These are kind of nice. These allow us to tie into the front of the video card and reroute the connections to the back of the case so you don't have wires hanging over. It's just a little nice little touch. Now, to power all this, because we're going to overclock your CPU, and we've got 2 GPUs running, we're going to be banging this thing out at a pretty substantial amount of watts on this thing. We're probably going to be pulling somewhere around 700 to 750 watts under load. So there's no kill like overkill. So this is a really great power supply. It's a 1300 watt EVGA rated gold power supply. It also has an eco fan setting so that the fan on this power supply will not kick in unless it needs it, and in most cases with the load we're putting in, it won't need it. So I like having somewhere around 30 to 40% extra on my power supply than my load. I wouldn't put a 1,000-watt power supply in this because we're drawing too close to the limit. And I don't want my power supply working at max, so that's why we use these. I put 1,200 as a limit, as a low limit on these systems, so 13 is right in line with that. Now, the fans we're using on the cooling, really cool stuff. These are EK Vardar fans. They're 1,850 RPM each. They're relatively high pressure fans. They're meant to work. They're meant to push a lot of air through radiators. If you put a low pressure fan up to a radiator, the air will come out the back. It won't go through the radiator, but the propellers on this are designed to press through into the radiator. They're also extremely quiet fans, and the wires are shielded. They're PWM fans, meaning that the motherboard can read what the RPMs are of this fan and adjust accordingly, so we can set curves based on our temperature. We can say, well, when we get to be 40 degrees centigrade, I want my fans at 50%, and at 50 degrees centigrade, I want to take my fans to 65%, and so on. So these 4 Vardar fans will be attached to the Hardware Labs 480 millimeter radiator. This is SR2 Black Ice. This is their most advanced radiator that they make. Hardware Labs is renowned for their cooling ability, and if you do a check on this radiator and compare it to others out on the market, you'll find that it is absolutely on top of the scale. So Vardars for the radiator. So we're going to have some very dependable, very quiet cooling. Now this radiator is designed to operate perfectly with 800 RPM fans. So why would I have 1850? I'm running 1850 fans so that I can knock these down to about 50%. So these things are going to run. You're not going to hear these at all. And in the event you want to really hammer this system and kick the heat up, we can run these fans up to 1850 and increase our cooling on the radiator just a little bit. I like having cooling headroom. Now we're also going to be setting this up with rigid tubing. We're not using flexible rubber tubing in the or plastic tubing in this system. This is PETG. It's like acrylic, and it's a clear tubing, and we have to heat it and bend it and fit it, and it's going to be using anodized aluminum fittings with O-ring seals so that it is extremely dependable. You guys should be able to see the coolant in it and the flow, but it's super clean and it's super strong. It's a lot of work to do these, and we'll get into tubing bending and how we're going to lay this system out later because everything is custom. I'm also a big advocate of, whenever possible, I will make a bend in the tubing rather than use a fitting, because every time you have a fitting, you have a potential leak spot. You know, every time there's an O-ring connection, you have a potential for a leak if the O-ring isn't tight. So I like the idea of actually putting the bends in the tubing itself. It can't leak. So there you have it for that. Now the pump. Just briefly. Okay, I talked about redundancy before. EK is renowned. They are the top of the line as far as water cooling goes. There is a pump, legendary pump, called a D5. It is a brute. It is designed to run all the time. Now, EK came out with these D5 pumps that have PWM, so they've got this beautiful fan control. So we can set the pump speed based on the temperature of the system, so we don't have to have the pumps running at 24/7. This is a dual pump setup, so you have both pumps running in serial. So what we can do is we can set one pump up to run during the normal temperature scheme. So we can say we wanted it 25% at low temps and 50% at medium temps and 100% at high temps. And when we start getting up into our high temps, we're going to have pump number 2 kick in. Now pump number 2 will add to the cooling, so it will increase the amount of liters per minute that they're traveling through the system. It also picks up so that if this pump were to ever fail, and the temperature started to go up, number 2 pump automatically kicks in. You don't even think about it. Now, in order to, this is so awesome. This is crazy expensive to do this, but it is beautiful and elegant in that it is silent, it is compact, it is designed to run forever. I've covered the wires, I've shielded them. We're going to insulate this with acoustic material. It's going to be beautiful, but I want to know that this thing will run no matter what you do to it. Now, let me go a little bit further on down the line. So that was the water pump, beautiful thing that it is. Now the water block. I decided we're not just going to cool the CPU. EK just came out with this, what they call a mono block. And what this does, it doesn't just cool the CPU, it cools the VRM, the voltage regulating module, which they're notorious for getting hot, especially when you overclock them. So what this block does is it covers both the CPU and the VRM. It's an active cooler, so I've got one with a clear acrylic top, polished nickelback, so that the fluid comes in, it circulates around through everything and cools everything down. So instead of having a fan on our VRM, we're going to run an active water cooler on that as well. It doesn't require any more plumbing, it's just one nice integrated block that fits on there, and there's no moving parts in this at all. It's just a heatsink that gets cooled off with the water from the radiator. Now, water from the radiator, that brings us to a couple of things. One of them is a choice of coolant that I'm using. Okay, this is from Coolants. I like this stuff because it has the highest rating for shelf life. In other words, this coolant could survive in your case for a couple to 3 years without having to be changed, without needing to be changed. Most of them require changing in about a year. I chose a UV reactive blue simply because I thought it would be, clean in the case. I'll do all of my testing with distilled water with a biocide, and then this is for the final fill. I've got 3 liters of this that'll go into the system. One of the important parts of this is that the water channels in the radiator, but primarily in the monoblock, are pretty small. You can't afford to have any debris caught up in the system at all. Now, before one of the last videos we did, we flushed the radiator, and I flushed it and flushed it and flushed it to make sure that it is absolutely crystal clear. Every component that we put in here, the pump, the tubing, everything gets flushed prior to being installed in the system. That being said, there's no kill like overkill. So here's this beautiful filter by Aqua Computer. It's made in Germany. It has 2 valves in here so that we can turn off the in and out or turn them back on. So this way you can service this filter by turning these off. You can remove the glass cover, not plastic, remove the screen, clean it, put it back, and then turn your system back on. So this is a way that you can, once a year, open the back of your case, look in this window and check it. Say, is it clean? Is it clear? Fine, leave it be. Has it got debris in it? Good. Open the window, take it out, turn it off, take your filter out and clean it. You're done. It's a really neat setup. You don't have to drain your loop. Normally with a filter you have to drain the loop and then remove the filter, and it's a real pain in the arse. So this is going in. Now, in order to monitor your flow rate, I want to see at a glance, I always want to see at a glance, what the flow rate is on the front of my computer. So what I do is I install a flow meter. This is also made by Coolants. This is a little impeller that hooks up to the water cooling system and sends a signal out to this device, which will sit in your front bay port. When this is connected, okay, this will display a backlit LED display. This will display in liters or gallons per minute what your flow rate is. It doesn't give you temperature, it just gives you the flow rate so that you can then monitor it. And you'll see if we set a fan curve on here that says, hey, run my pump at 50% until my temperature gets to be 50 degrees centigrade. So when you're idling and you're at 25 degrees centigrade, you'll see this and it might say you're only running at like 1.2 liters per minute. So you realize that it's running slow. It doesn't need to run fast because it's already cool. When you're running one of the programs like Zareen Stacker and you've got a 100 image stack and this thing is really crunching and the CPU is running at 80-90%, the pump will kick up a little bit and you'll start to see, hey, you're running at 4 or 5 liters per minute. And you can watch how this thing travels. You always want to make sure that there's flow rate through here. If there is no flow rate through here, you have a problem. It means the system's going to overheat. There is an automatic shutdown on this. It won't allow the thing to burn up if it does overheat, but that's really unlikely. This is just a way you can monitor your system. I really love these things. And again, this little thing, it gets flushed out. Everything gets flushed out. It's also pre-tested. I've gone ahead and I've run it through and I know that the impeller is accurate. So there you have that, sort of a flow rate sensor. I'm going to put this down here. I'm making a massive pile. All this is going to fit in that little box, believe it or not. Oh, your reservoir. This is going to be cool. I'm going to cut a hole in your lighting panel and sink the reservoir down in there. Okay, this is a Thermaltake Pacific. I love these little things, they're cute. Okay, so here's the reservoir. It's going to bolt up to your back panel. I'm going to put a hole in your light panel so the reservoir actually sits down in there. Here's a fill port. This is where the water or the coolant comes in. It comes up this tube so it doesn't create turbulence. And this is where it exits out. You won't even see these plugs because they'll be below the surface. There you go. I think this is a 200 milliliter. No, 300 milliliter capacity. Woohoo! Okay, so we got lots of capacity for the coolant there. Again, this all has to be mapped out before we drill any holes. I have to mount everything and measure everything and make sure it's in the right spot, because once you commit and you drill a hole, you're done. A couple other things I got some aluminum stays for the video cards. These things are huge, the video cards, and you don't want them to sag in the PCIe slots. So these clip onto the carrier or the motherboard and lock the video cards in so that they stay straight. Your optical drive. I opted for a slot optical drive reader. So this is a really cool, this is again made by Silverstone. It's all aluminum. It's just a little slot. So here's your slot optical drive. It's going to go in there. And underneath it, it holds some solid state drives. So I'm going to put your primary image drive, your clone drive in here. The primary image drive is an M.2 and so is the boot drive. They go directly onto the motherboard. And your the Western Digital drive will be down below in a vibration isolated carrier. So this is your slot drive, really clean. Also, you're going to get a card reader. Yep. Another USB 3 port and a card reader slot so that you can read your cards from your camera. You really don't need this, but I figured why not throw it in there and make it future proof. Now this is again a Silverstone all aluminum front bay converter. It converts your 5 1/4 inch bay to 3 1/2 inch bay. I just want them to match perfectly, so because I've got the optical drive from Silverstone, I wanted to get the bay converter from Silverstone. Just to give you an idea, you can get a plastic bay converter for about $3, or you can pay 30 bucks for one of these. But you know, it's no sense in scrimping nickels and dimes when you're talking about a system like this. So lastly, here is the ejectable hard drive that will go into the front bay, and it just pops right in there. And this is wonderful. You've got basically a 500 gig portable drive that you can pop out and place wherever you need it. This is your serial port adapter that's going to go in there to allow you to have connections to the lift, to the cam lift. And lastly, I've got some SATA cables. These are really cool. These aren't like regular SATA cables. These have locks on them, and they're all braided. Okay, so that all the braiding, I've got them in graphite, which is this graphite. I love this stuff. This graphite is the color I'm doing on your wires. I've got a couple of black ones too, so that they differentiate, so that I know that my optical drive and my portable, my ejectable drive are black. My SATA drives for the clone and for the Western Digital 10 terabyte drive are going to be carbon. So I can see what they are at a glance. These cables, this is a custom set, if I can open the box. So these cables, for instance, are all individually sleeved. Each wire is individually wrapped up into the plug, so there is no color, there's nothing exposed. These wires give me the added flexibility. When you have one cable that's all wrapped together, they have a tendency to be pretty stiff. With these, I can lay them out with a loom like this. I can lay them flat like so they take up less room. They're really, really nice. They're also extremely durable, these cables, so it's not that you're going to be moving them around anywhere, but I wanted to be able to have cables that I could tuck in and tie out of the way and have them look really clean. So again, functional artwork. So there we have it. This is going to require a bit of working and measuring, and I trim these too. If a cable is way too long and I only need 6 inches and I've got 2 feet, I cut it. And lastly, the operating system. Windows 10. Don't love it, but it is what it is. This is the Windows 10 Pro 64-bit. We got to use it. So Microsoft's kind of got you by the short and curlies on that one. I prefer Windows 7, but it's not going to be supported anymore, and so there you have it, Windows 10. That's about it for now. There's a bunch of other keyboards and my... Okay, back again. I set up my test bench and ran the motherboard and the CPU and the memory. I installed Windows on a test bench just to see what kind of temperatures we were going to get and at what overclock. So I've documented everything. I've run Blender, I've run Prime 95, I have run CPU-Z, and I have run Cinebench. I've got some scores here, and basically I am thermal limited. I cannot get this thing past about 4 gigahertz. Stock on this is 3.8, and so what we're finding is that it's just getting really hot as I crank this thing up. So that's why we're going to go ahead and delid the CPU. But I wanted to get pre-delid. I always do this. I always put it in and I run through a whole series of tests prior to delidding it. I want to make sure we're okay. We also have a delta of almost 22 degrees between a couple of cores here. Between core 1 and 7, and then core 8 drops way down. So that's not totally uncommon with the X299 platform. However, that's just a bit of an extreme. So it may be something to do with the way the original thermal paste is set up. So we're going to go ahead, even at stock, I'm getting temperatures at stock of 83 degrees Celsius, running this at 100%. That's with an ambient room temperature of 25. So that's a bit on the hot side. So I'll go through what's necessary to delid the CPU next. Here's where we are now. I've gone ahead and I put this on my test bench So I've got the memory, and I had the CPU mounted, and I've got the graphics card mounted. My power supply is hooked up. I'm running a Corsair H150i. All-in-one cooler is what I use for my test bench. I put a little Samsung 500 gig drive on there. I threw Windows on there. It's running Windows 10 and all my my benching software. So what we're finding, I'm running Cinebench and I'm running Blender as a couple of ways to get some constantly high temperatures in here. I've run the Intel Extreme Tuning utilities to get an idea also of my temperatures and hardware monitor. So even at stock speeds out of the box, this CPU is giving me, it's idling in the high 40s. I'm getting temperatures at 100% of as high as 83 degrees Celsius with a VRM temperature of 60 degrees. And that's running at 3.8 gigahertz. If I crank this thing up to 4.1, I am then getting temperatures 98 degrees Celsius, which is way too high, so I don't even bother running it through. Cinebench scores are quite respectable. This thing kicks ass. It's just a matter of getting the temperatures down. So to normalize, oh, and also to the delta between the cores, I've got cores 1 and, let's see, let me double check my information here. Max core, core 1 and core 5 were my hottest cores. Core 8 was my coolest core. So I had as much as a 17 degree difference between core 1, core 5, and then which were the same, and then core 8, which was the one that was off. So I'm thinking that I've got potentially some funky thermal paste under the hood on this from Intel. We're going to open it up and find out. Before we get started on this, I wanted to briefly go through what we're going to do to the CPU. Here's the CPU here. This is the heat spreader. Underneath the heat spreader is the die. That's the actual chip on the board, on the PCB board. So what we're going to do is we're going to put it into this device, which is a tool that will remove the heat spreader from the top, which is siliconed on to the board. So once that's popped off, we can get underneath there. We can clean out all the silicone. We can clean out all the thermal paste. That takes a bit of doing. And we're going to replace the thermal paste, the stock thermal paste, with this. This is made by Thermal Grizzly. It's called Conductonaut. It is a liquid metal. It is. This will allow the heat transfer from the die to the heat spreader to be extremely efficient. So we should be able to get a drop of between 10 and 15 degrees on this, certainly on some of these cores. The other thing we're going to do is we're going to lap this. We want to, I'm basically going to sand the top of this heat spreader down flat. I'll bring it to the bare copper. I'm going to start out with 600 grit, wet and dry. I'm going to work my way up to 800, 1200, 1500, then I'm going to go to 2000. Basically going to give it a polish so that it is going to have an absolutely flat, blemish-free surface to get into my heat sink with, and we'll get into that too. So it's a fair amount of work. We're going to be using rubbing alcohol. We're going to be using a special cleaner, Q-tips, orange sticks. This material here, this is a lacquer, an acrylic lacquer that we're going to take a little tiny camel hair brush, and we're going to be covering the capacitors and the resistors that are all around this die to prevent them from being conductive. So liquid metal is conductive, and we don't want to take a chance on shorting anything out. It's a process, but it's a worthwhile process. We'll get into that in a little bit. Okay, here we are back. Now we're going to go ahead and pop the top off of this, off the CPU. On my Rocket 99 CPU delidding tool, it has a little triangle right here. That coincides with the triangular mark right here in the corner of my CPU. It's critical that I mount it this way so that I don't rip off capacitors and things inside the CPU. So it gets placed in the device like so. The top is going to be put on. It has a metal block that's going to slide over and pop this top off. So I slide it all the way back. I place my block on top here, and I'll secure it with the 3 screws. You want to tighten these down, but you don't want to over torque them. You want it to be able to move a little bit. But you don't want it to slop around either. Just snug that down. I'm going to take up the play with my fingers. Then I'm going to put the hex wrench in there, and I'm going to start turning. When I hear a snap, I'm going to stop immediately and back it off, remove the top, and access my chip. Go slow. That's it. Back it goes. There you go. No harm, no foul. Now there you go. That's a that's a lidectomy on a $1,400 CPU. Yeah, it's always a little unnerving to do this, but now we're going to go ahead and I'll bring the camera a little bit closer so I can show you some of the detail. Okay, here is our heat spreader. You can see the original thermal paste. It's kind of dry and crappy. It's not that great sitting around the top. This black material is the silicone that's used to glue the heat spreader onto the substrate. This is the die. These are little tiny electronic components that you can flake off really easily with a fingernail. Don't want to do that. Look how small those things are. And you know that the way you know this heat spreader is on correctly too, I'll show you. The heat spreader has only one corner with a cutout. There's a small RFID chip right here. That cutout mates with that RFID. Now when we put it back, I've got a special jig that will line the heat spreader up perfectly with the die, so it's absolutely on. What I'm going to do first is I'm going to take some solvent and I'm going to remove this thermal paste off my die, and then I will go ahead and I will clean off all of this silicone, and I'm going to use this orange stick because this will allow me, and I'm going to leave my CPU inside of this. This will allow me a way to get in here and sort of peel off this crud without causing any major problems. So I just work it around, work it around. I don't want to scratch the board, obviously, and I'll get to a point where I'm ready, and then I'll take some alcohol on a Q-tip and I'll wipe it off. When I'm all done with that, I'm going to take this camel hair brush and some of my acrylic lacquer, and I'm going to just basically cover these electrical components here so that I'm putting a very highly conductive material, my liquid metal, on top of here. Should I put too much on and something touches these two components, it'll short out the CPU and it's $1,400 down the drain. We don't take chances like that. So this is used for remote controlled planes and boats and things like that that would be exposed to moisture, and it's specifically designed to protect electronic components on circuit boards. So that's what we use. Okay, so I'm going to get cleaning this up and I'll come back with a video and show you the lid cleaned up. Before I put the lid back on, I'm going to take this and I'm going to lap it. So I'll show you the lapping process before we glue this back on. But let me go clean this up and I'll come back. Here's the CPU. Here's the die. You can see how it's all clean. Here's the heat spreader. It's all cleaned out. All of the silicone has been removed all the way around and on both ends. It took a collection of Q-tips and wooden sticks and little things to clean this up. What I use to soften the silicone is this Arctic Clean thermal material remover. It cleans off the thermal paste. It also helps soften the silicone so that we go through it with a wooden stick and it just sort of, it peels right up. And then I follow it up with 91% rubbing alcohol and wipe this off. I want to make sure that I maintain my CPU clean at all times. I typically don't lay it flat on the floor, or on the table, because the back of the CPU has this has these components, and you don't want to put a lot of pressure on these things as you're putting it down on the table. So I like to keep it into the die, which gives it a space on the bottom. I'm going to go through now, and I'm going to just cover these with this acrylic lacquer, give you an idea how that works. I take a little tiny bit on my brush. I'm going to take my glasses off so I can see what I got going here. Just a little tiny bit. I don't want to flood it on there because I want a little bit of control over it. So I'm just covering each one of the tiny components as an extra added safety measure. Hopefully it's not even necessary. But you know what they say, there's no kill like overkill. And if you can do it, do it. My thoughts on this are, now that it's open and accessible and we have at it, there's no time like the present to take care of this stuff. You don't want to have to come back and say, man, I wish I'd have covered those up because for whatever reason I have a short. That would be a problem. And this material, it just completely covers it, encases it. And it's an acrylic lacquer, so it's a synthetic lacquer. It does not hurt the substrate. And I like the fact that this is used in the industry by thousands and thousands of people for exactly this purpose. So I'm not trying to experiment with some new idea here. I'm simply applying something I know works. So that's it. I'm giving everybody just a little bit of a bath in this, and then we'll call it a day. Here we go. This dries really quickly, so you have to kind of be careful how you work. It's better to put on a couple little layers, a couple little thin layers, than it is to overdo it and goop it up. Yeah, we're good. Okay, so that's it for that. I am going to put this aside and let it dry thoroughly. I'll put a cap on it. This cap, this way. And then I will set it aside and I will start working on my heat spreader. This thing from the factory is pretty dimpled and warped up. I was looking at this, we got a really big low spot here. There's an area here, a little dimple left there. You can tell by the pattern between the nickel and the copper where the high points and low points were from the factory. This is really cattywampus. Now, I was a jeweler, goldsmith, and a setter for almost 2 decades prior to this, so I know how to lap and I know what I'm doing as far as making things flat, how to hold it, rotate it, and pressure and put different pressure. I'm going slow and easy. The primary goal here is flat. It isn't speed, it isn't polish, it's flat. And this is really showing my high and low spots. So this means that we need quite a fair amount of thermal compound if we're going to be able to have this entire structure touching our cold plate. because of all these little low spots. So I'm going to go continue on until I get almost all copper. And then I'm going to switch back to, I'm going to switch over to the 800 and 1200 and 15 and 2000. I don't want to go too far down because I don't want to lower this too much, but I'm going to continue on and get some of these low spots out. Okay, I finished up with a 600 grit for now, as far as I want to go with it anyway. What I found is here, we have a divot here, 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 and here. It's part of the casting, and it's still a low point, but all of my scratches are going up and down like this right now. That's 600 grit. So I'm going to switch over to 800 grit, and I'm going to start sanding it this way. Ultimately, I'll end up getting these out of the way, but I don't want to rip it all up with 600 first. So what I'm going to do is I'll put my 800 grit down. Actually, I'm going to put a little water on it so it sticks. And I'll put a little bit of water on the sandpaper. Okay. And I am going to be going this direction. So I'm going to get it started. And I'm going to hold equal pressure on this. And I'm just going to keep walking it back and forth like this. And I'm going to be keeping as even pressure as I possibly can on this. And I'll flip it around the other way. Again, but I'm still going in the same direction with my scratches. The reason I want to do this is because I'm going at a right angle to my previous grit, so that when I have fine scratches only in this one direction, I know I have eliminated all of the 600 grit scratches and I only have 800 grit left. And then when I cross these with 1200 grit, the same thing applies, and with 1500, and finally with a 2000 grit, which will give me sort of a mirror finish. So I'm just going to be very patient and go back and forth with this thing and take my time with it and make sure everything gets nice and straight. Again, being flat is more important than speed or anything else. I'm just going to take a quick peek. Now I've still got some scratches going this way here. So I'm going to continue on and get back to you when I have nothing but copper. And I'm going to do that with 800 grit, and then I'll transfer over to a quick sand and polish with 1200, 1500, and 2000. That's the easy part. Getting it flat, that's the hard part. We just finished our final sanding of the heat spreader here, and it is perfectly flat. You see all my scratches are going in one direction. It's nice and shiny. It's super clean, and it's going to be ready to go on to our die in just a minute. All right, that's it for lapping the heat spreader. I've gone ahead and I put liquid metal on my heat spreader, right where the die is going to be. I went ahead and I put liquid metal on the die. Again, I'm being careful not to overdo the amount of liquid metal on the die. You don't want to puddle it. You know, you don't want to have like mountains of this stuff. It's got to be a really thin coat, and obviously you don't want any debris in it. So I'm just wiping it through. I'm going to lay the die in position now, or the heat spreader in position. I have put my jig on here so that this thing should fall right into place. Right there is exactly where it needs to go. And I'm going to put my Alright, I am going to let this thing sit overnight now and let the silicone dry. I'm using this stuff here as Permatex Ultra Black High Temp Gasket Sealer. We're done. As far as this CPU is concerned, tomorrow we'll put it into the machine and fire it up and see what we get. This time I wanted to talk about the monoblock that I had gotten for this motherboard. This is an EK monoblock. The idea behind it is that it cools the CPU and the VRM. I took the cover off the VRM so you can see the heat chokes up here, the chokes that get hot rather. And that would be cooled down here on this bar, and this is the area for your CPU. This is our lapped copper CPU sitting in the box. I'm not going to go for the monoblock. What I'm going to do instead is I'm going for the best CPU cooler that EK makes. It's called the Evo Supremacy. You can see here the surface area is much larger than the circle on the monoblock, so you get a little bit more heat dissipation in theory. I don't know if that really translates to anything. I've used this block many times. It is a proven performer. It is awesome. Now, one of the reasons I love this block too is that it comes with 3 jet plates. These little, they look like razor blades. They sit over the top of this base and direct the water down over some micro fins. And it has a couple of different inserts. Now, what's cool about this is that you can tune it per CPU. The manual lists half a dozen different CPUs with different combinations of jet plates and inserts to optimize the cooling. And so what we've done is we've optimized this for this CPU so that it's dead on. We still want to cool the VRM. I could use the stock air sink for it, air cooler, which is okay. But I know that my VRM temps are going to get up into the 70 degrees. Look, they're designed to run hot. That's not a major issue. But while we're here, if we have a chance to do it really well, that's what we want to do. So the back of the VRM has a plate that goes up against a couple of components. Let me turn the motherboard around so you can see it. These components here on the back of the motherboard will need to be cooled off. And so the way this is set up, this little heat sink screws on the back of the motherboard right here and covers those components with a thermal tape and this aluminum heat sink. Now, the thermal tape that we use is called Fuji Poly, and it is the best thermal tape made. We use the Ultra Extreme edition of thermal poly, which is the best money can buy flat out. This has the best conductivity of heat. So what we're going to do also, we're going to add an active VRM cooling to this, meaning that we are going to water cool the VRMs, but we're going to do it in a specific order. So if I have my CPU sitting here, and I've got my water coming in and my water coming out, I now have this, which is a heat killer. This is a German block that is nickel plated copper on the bottom. Now, you see these gray pads I have on here? That's Fuji Poly. This is the stuff that it comes with. It's kind of a bluish color. Now, everybody that sells thermal pads like this, especially on active coolers, they use the cheapest stuff they can, because this is a couple of pennies. This is $20 a strip. It's insanely expensive, but it is the best that's out there. So if you're going to take the time to do this, why not just spend a couple extra cents and do it right? That's just my opinion. So we've taken the stock thermal pads out of the equation and replaced them with the the Fuji Poly. So it's basically Fuji Poly all the way around on this one. So what's going to happen is this block will now sit here. Let me move the CPU out of the way so you can see it. Will now sit here and cover the VRM. It gets attached underneath with a couple of screws like this, which will hold on this heat sink again, so it's sandwiching the motherboard between the active cooler and the passive cooler on the back. So the way we're going to set this up is we're going to have water coming into our CPU out of the pump. So that will be our first component cooled. This is the one we're most concerned about. Then after the water leaves the CPU, it will go into the VRM. The VRM has a tendency to run much hotter. So if my CPU, I want, it's down in 30 degrees and my VRM is up to 50, it makes sense to cool the CPU first. I don't want to preheat the water in the VRM and then run it to the CPU. And that's another thing about this relative to a monoblock. The monoblock has direction in that the water comes here. It circulates over the VRM and it's supposed to exit here, but it is still connected to the CPU water loop. So this water can circulate around and get warmer. It has been noted that when using the monoblocks, the CPU temperatures can be a couple of 3 degrees centigrade higher than when using this. And the idea is, well, you're getting active VRM cooling, so that's okay. I want it all. So what I want is the very best cooling on my CPU and the active VRM cooling. And basically I'm isolating them this way. So that's where we're going to go with this. I'm going to go ahead and mount this. It's a very simple process. We just pull the protective coating off the Fuji Poly and place it down on here. Now the Fuji Poly comes in different thicknesses, 0.5 millimeter, 1 millimeter, 1.5 millimeter. It's really important to get the thickness right because you don't want these things squishing down over the electrical components. All they have to do is contact them. So the original pad was very specific with this. It is a 1 millimeter pad. So we replaced it with 1 millimeter Fuji Poly pads. So there you have it. The CPU, we're going to use Thermal Grizzly, just like we always do. This is going to go on. It's very nice. This is also solid nickel. It's copper with nickel plating on it. The thing weighs a freaking ton, but it'll never crack or mess up on you or go cloudy. I do like the fact that it does have this big, super flat, highly polished contact surface for the CPU. So that's it. I just wanted to bring that up to speed and why I chose not to use the monoblock. The monoblock is a beautiful thing. I just thought that since we're at this point, and I've had such tremendous luck with the Evo Supremacy water block in the past, and it's regarded as probably the best water block out there. I do like the way that it's tunable, and I did contact EK directly because their manual does not list the latest 2066 CPU in here. It lists an older LGA 2011-3, and EK did tell me that you use the same jet plate and the same insert for this one because internally the size of the die is virtually identical. So that's been verified. That's it. I'm going to go ahead and put this together and then we're going to get it in the box. Well, some good news. I went ahead and I put the CPU back in there. Again, I'm just doing my baseline test with the Corsair H150. And we got this thing going in there. Now, I'm going to show you, or tell you some numbers I got. On the last test, when I did this, I ran it with a XMP profile active, so it was at 3200 megahertz on the RAM. We're at 4 gigahertz, so we had it at 1.125 volts manual. I have an AVX offset of -1 and an AVX 512 at -2. That was my overclock setting the first time around. And the reason I had the AVX backed off is because even with that, and at 4.1 gigahertz. Even with that, my high torque core temp was 98 degrees Celsius. That is way too high. Okay, we're a few degrees away from thermal throttling, and certainly too hot for a daily driver. So, but I wanted to see how far we could push it and keep running. And the whole thing is the voltage. The higher you run the voltage, the more heat you get. When you run a higher overclock, you need to boost the voltage. So we're going to tweak the overclocking. But here's the deal. Oh, and then Cinebench. I got a score of 3173. My maximum temps were 78 degrees. When I ran IDA 64, again, my maximum temp was 98 degrees. That was on core 5 and core 1. They both hit 98 degrees. My VRM was 68. Stock, out of the box, my VRM was 60, and my highest temp was 83 degrees. That's running just at 3.8 gigahertz out of the box, no XMP, no nothing, just very mild. Now, after we went and delitted this, and you saw me lap the CPU, again, this is just with the Corsair factory thing. This is there's no lapping done on this. I went ahead and fired it up. My idle temperatures, with the same ambient room temperature, my idle temperatures, all the cores, are between 25 and 28 degrees Celsius. That's a 3-degree difference between the cores, which is great. Now, when you throttle it, when you run this thing at 100%, that's when you start to see big differences in the cores. Now, in my initial run of this, with that first overclock, I had a spread of 14 degrees between core 1, which was 87 degrees, and core 8, which was 73 degrees. Now, let's see. With the new delitting, my Cinebench will start off with that first. Again, same overclock settings as before. I got a 3177, slightly higher score. My maximum temp was 64 degrees. Okay, that was core 1. That was 64 degrees as opposed to 78 degrees. So it was a 14 degree drop in Cinebench. My coolest cores were core 8 and core 10 at 57 degrees. So I've got a 7-degree difference at 100% throttle as opposed to a 14-degree difference. So now my core temps are much closer together. That's telling me that I'm making better contact with the heat spreader. Here's the big one though. IDA 64. Okay, when I ran this thing, initially it was 98 degrees, was my highest core temp. With this now, my highest core temp is 74 degrees. I've got a 24 degrees Celsius difference, which is massive. Now, we haven't put in the 480 millimeter radiator, which is twice as thick as this and much longer. And we haven't run the really high-end EK water block either. We've got this, okay, kind of crappy water pump block. It's okay, but it's not like what we've got, not like the high-end one. So, success, big time. We have a huge drop in our core temp using the same overclock settings, the same ambient room temperature, and the same cooler. So I'm thrilled. Now, when we go to overclock this, we're going to be doing a number of things. We're going to be adjusting the power setting. We're probably going to do this per core. I will pick the very coolest running cores and I will juice those a little bit more. I will take my hottest running cores, which are 1 and 5, and I will dial them back a little bit. So when I'm overclocking, I might overclock those to 43 or 44, whereas the other ones I might take them up to 47, depending on what I can do. And I'm going to do a type of an adaptive voltage on this, so that while it's idling and it doesn't require a lot of throttle, the voltage is lower. So I'm not hitting all the cores with 1.2 volts all the time. I can only hit the cores with a high voltage when it needs to overclock. This will keep the everything cooler. VRM as well. It won't be putting as much voltage in. So I've got quite a bit of tweaking to do on the overclock. I'm probably looking at 8 to 10 hours of playing around with this overclock to get the settings right. But the point is, we can now do this to the max because we've got such a dramatic change in this with our liquid metal and our lapping. So I'm very, very happy with that. It is a little disconcerting every time you pop the top on a $1,400 CPU. You stand a chance of eating it right there on the spot, and it's a lot of money to absorb but I think the risk is worth it considering the benefits that we gain from this. This isn't my first rodeo. I've done a few of these D-lids before. I've learned what to do, what not to do. So all is good. Let me get off on this. I am going to finish working on some things in the case, mounting the reservoir on the motherboard tray, setting some fans up, and we'll put this away for now. I'm good with this. I think we're going to take it off the test bench and move it into the actual case. The next thing I'm going to do is I'm going to take the VRMs off of this board. Not the VRMs, I'm sorry, the VRM heatsink off of this board, and I'm going to perform the operation of putting on the monoblock, which is a bit of construction, and we'll go through that together on a video. Okay, we finally finished. The TJ07 is now assembled. I'm going to zoom in a little bit and give you a close-up on what exactly everything is, how it works, how to maintain it, and hopefully answer a few questions. This is an overview of the components installed. I'm going to use a little laser pointer just because it's easy. The motherboard is in. That's the Rampage 6 motherboard. The memory is in. There are 4 DIMMs here. This is the G-Skill Trident, 3200 megahertz memory, 64 gig of it. The clone drive is in one of your bays behind here, actually. The slot DVD reader in front here, underneath it is the solid state drive for your clone drive. The switch for your clone drive is right here, designated by the sticker that says clone drive on and off. You turn it on and you turn it off, and it's illuminated when the machine's plugged in. It lights up and there's pictures in your manual. This is your CPU block here. That is, this is the cooling block, and the way this is set up is this is your 480 millimeter radiator with the 4 fans. The water from the radiator goes into the reservoir, out of the reservoir, up this tube, along the tube, here into the CPU block. It cools the CPU, it goes out of the CPU block, it goes into the VRM cooler, out of the VRM cooler, back into the radiator, it gets cooled. And on the back side, I will show you the pump and the filter and the monitor that measures the flow rate. Your primary image drive is a 2 terabyte Samsung 870. Is on this card right here. It's air cooled. This is a special card slot that's only available on this particular motherboard. Your boot drive is underneath your bottom graphics card. It is under a shield on the motherboard to protect it, and it also keeps it cooler. This is your water reservoir right here. This is, right now it's full of distilled water with what we call dead water, which is a biocide to prevent growth inside. When it's all said and done, it'll be filled with a special coolant that should be good for about 3 years on you. Tucked here on the inside are 2 gauges. I don't know if the camera can show this or not. Once these are lit up, they're illuminated. This is a temperature gauge for air, and it measures the air temperature exiting the radiator. And this is a temperature gauge that actually measures the water temperature, and it's connected to one of these temperature probes on the radiator. The radiator has 2 temperature probes. One goes directly to the motherboard and one goes to the gauge. This is your 140 millimeter intake fan down here. That's bringing in cool air into the case through the front of these filters. Let me talk about the front bay drives briefly. This top bay drive is kind of cool. It's a removable front bay. This is a cartridge that has a 2 terabyte solid state drive in it. You push it in. It's now operating off of SATA, not USB, so it's directly to the motherboard. It's a hot swappable drive. You can plug it in and unplug it anytime during normal operations. It'll show up into your My Computer and you'll be able to see it. It's basically a fast data transfer drive. This is so that in the event you want to pull off a lot of big images off this machine and take them to another machine, it's like a thumb drive on steroids. So you've got 2 terabyte here, and when you're done with it, you don't even have to hit eject. You just press this button, take it out. And this has a USB 3 cable. This can connect to any computer with a USB port. Below it is your slot reading DVD drive, CD DVD drive. Housed below that drive is where your clone drives are hiding. This is your card reader with a USB 3. This device in the front is a this one. This is a flow meter, and what it does is it measures how many, we've got it set up for liters per minute right now, how many liters per minute your system is pumping through. You have two water pumps. Your primary water pump is going to pump at about 3.7 liters per minute. The secondary pump, if it kicks in, it'll bring you up to 4.5 liters per minute, which is quite a bit. The idea of a second pump isn't to increase the speed, because 3.7 liters per minute is more than enough. 3.2 is fine. It's in the unlikely event that your primary pump fails or has a problem, the secondary pump automatically kicks in. Because as the temperature increases, that pump will start kicking. And that's it for the front bay devices. Oh, hidden behind here are your USB 3, Type A and Type C, your microphone and headphone jacks as well. This is a little magnet that closes that door. To release it, you just press on this button and the door pops down. This is your power button. It's a hard light indicator. Let's see. Let's take it around back, and I'll pop this cover off the case. Pardon me. To get the covers off, while we're at it, we might as well talk about the back. This is the back. This is your IOs. These are all your USB 3 drives here. This is a power USB 3. There's a USB 3C. These are headphones, microphones, stereo speakers. These are the two graphics cards. We have one here and we have one here. This is the primary graphics card that you're going to be working off of. These cards are in SLI configuration. They're joined together by an electronic bridge. You don't put any monitors in the bottom cards. Up here you can fit as many as 3 monitors at the same time. You've got a DVI, you've got 3 display ports and an HDMI port. These are your serial ports. You use one of these for your lift. Your power supply, on off button down there, and that's and this is a dimmer control with an on off switch that will control the intensity of the light for your backlight, and we'll do a video on that in a little bit. So to get these panels off, you simply unscrew these thumb screws that hold the aluminum panel on the side, and then you pull back and the panel slides right off. This is sort of the naked side. This is your 10 terabyte data drive sitting there. Down here in the bottom, I use these custom wires because they afford me the ability to fold up without kinking. This is a dual water pump. There's one here and there's one there. They're joined together in the middle. So these two D5 pumps, this is your primary pump, this is your secondary pump. They're going through a filter here. This filter has 2 ball valves in the back that you can reach back and you can pull the levers to open and close them. The beauty of that is that after a year or so, if you ever decide you want to clean this filter, you do not have to drain the system. You simply turn off the ball valve of the intake and the out port. You can unscrew the front of this, remove the filter, clean it, put it back in, and then turn your valves back on and your system's up and running. Here's an extra port here that you could use for another auxiliary drain port. And directly behind this is the electronic flow sensor that has an impeller in it that sends the data to this device in the front. This is your power supply back here. The power supply here has a very large fan on the other side that is also drafting air from your radiator, and it's spitting it out here. So you've got air coming in and going out that way. So although the power supply itself is blocking the radiator, it is not blocking the airflow from the radiator because of this configuration. These others are open, and while the machine is running, if you put your hand over here, you'll feel warm air exiting the machine. You don't have to get into the business end of this. This is a drain. You know, I've got it kind of held in with a wire tie right now. This is a drain port. There's a cover on it. What this has a little petcock here, so that if I ever want to drain the system, about every 3 years you want to change your coolant. I would unscrew this cap. I would loosen the cap on the top of my reservoir. I would open my valve, and all the liquid would come draining out. No muss, no fuss. Put this over a bucket somewhere. When you're done, you close this off, you recap it, and you put it back. That's it. Again, you don't really have to do anything on this side of the box. And considering all the wires and where everything is, that's quite a lot of wires tucked away in here. I'm just going to close this off while it's seated, and that locks it in place, locks it up out of the way. Let's see, that's about it. The way this thing is working right now is it's sitting there with nothing on, no power, it's idling. I have it programmed so that the LEDs just cycle through their light. This basically tells you that there is power to the computer. It's not turned on, but you can see what appeared to be solid silver is actually translucent. It's like a two-way mirror, and it has a design that goes on behind it. If I were to go to start this thing up, hit my power button in front. Now it's starting to go through its paces. If I turn on my lights here, this is my backlight, and there's a little light in the reservoir, and this has a control on it so you can set it for high or low. It's just an aesthetic thing. And that's it. The gauges are inside. You can see them lit up now. So this is your air, and that's your water temperature. And that's basically it. I'll wait for it to boot, and then I can shut it down safely. There's a lot going on this motherboard. This takes a while to boot. This takes you, almost a full minute to boot the system up because of all the pre-post testing that this has to go through. It's a pretty complex piece of equipment. You can see your water rolling around in there. Now when you get this, you're also going to get some fluid. Let's see if I have some of that around here. Okay. This is the fluid that we're going to be using to fill your system with. It's made by Coolants. I'm also going to give you a couple liters extra so that 3 or 4 years down the road, if you want to flush it out, you'll have the same stuff handy. The other thing you're going to get is one of these, a little squirt bottle. There you go. And what this is for is that to fill this thing, you're going to remove the top of this reservoir cap, little thumb screw, and you're going to fill it with something like this so that you're not dealing with funnels and tubing and all kinds of stuff. This just makes it so much easier. That's about it. She's booted up. I'm going to shut it down. It's a very quiet running machine. All of your fans are currently running at about 50%, and that's all you need. If you really put this thing through its paces and you're doing some serious composite work, or stacking a couple hundred images, and this thing starts to really kick in, at that point you'll hear the fans ramp up. They will automatically increase. The pump will automatically increase. Everything is designed so that when the system reaches 60 degrees, everything starts smacking and it wants to cool itself way down. And that's about it. I'm going to shut it down now, and that's the end of that. Everything else is in your manual, by the way.